We study all these mass transfer operations, VLE, LLE, and SLE, and we study SVE also to study the limits of operations. What is the maximum which can be achieved, or what is the maximum mass transfer which can be done in these operations. In the real world, it's always going to be less than this ideal condition, and it defines how much we can improve. What is the limit of improvement which we can target? And when we look at solid liquid equilibrium, we are looking at process, for example, crystallization, where you take a solution which may have, say, salt, NaCl, then we evaporate it, make it concentrated, and becomes saturated liquid. What is saturated solution? याद है किसी को? Suppose I take NaCl and dissolve in water and make a saturated solution. What is it? What does it mean? याद है किसी को? कैसे रहोगे यार? भूल जाते, सेकेंड ईयर में पढ़ा, थर्ड ईयर में भूल गए, बी में क्या करोगे? You can't remember what you studied in second year, first semester. Then how will you progress to B? How will you remember all those things? Any guesses? Anybody wants to take guess? What do you mean by saturated solution of the NaCl in water? Devendra?
मतलब सर वो और NaCl नहीं ले सकता अपने अंदर.
Yeah. So if I take a solution, if I take water and heat it to say whatever temperature, say 40 degrees, 50 degrees, 60 degrees centigrade, and keep adding NaCl till no more NaCl dissolves, right? NaCl will dissolve up to the solubility of NaCl in water. There's always some solubility of salt in water at a particular temperature. Solubility will be less, solubility at 40, 50 degrees will be more. And these are properties of that salt in water. So if I take water at 25 degrees, NaCl dissolve थोड़ा कम होगा. If I increase the temperature to 40 degrees, ज़्यादा dissolve होगा. And a time will come, if I keep adding NaCl and maintain the temperature 40 degrees centigrade, उसके बाद NaCl dissolve नहीं होगा. Right? You will see crystals of NaCl at the bottom, and that is called the saturated solution of NaCl in water. Right? Just like we do PSAT. What is PSAT? VLE में? What is PSAT? We have done VLE इतना किया, पूरा सेमेस्टर हमने यूनिट 1 to 3 VLE में गुजार दिया. What is PSAT in VLE? ये पता किसी को?
Sir, it is saturation pressure or vapor pressure.
Saturation pressure. What does it mean?
सर मतलब वो जो गैस है वो कितना वो लिक्विड होल्ड कर सकता है इसके अंदर.
Right. So if I look at similar to what I talked about crystallization, we're talking about crystallization में NaCl in water. That is, solute is NaCl, solvent is water. वो dissolve कर रहे हैं, उससे saturated solution बनेगा कब? जब solubility यानी उससे यार dissolve नहीं कर पाएगा NaCl water में. Similarly, if I talk about air and water, the maximum which air can take water. Think about water as NaCl and air as water, similar to crystallization, comparing to crystallization. The maximum water which air can take at that temperature is saturation pressure or vapor pressure. उससे ज़्यादा वो water उस air में जा ही नहीं सकता. And that is why we have dew point. Dew point क्या है? What is dew point?
It
Sir, the
is the
temperature
point
at
where
which liquefaction
condensation.
starts.
7% at a time. बोलो वैभव नहीं बोल रहा है कौन बोल रहा था और दूसरा दीक्षिता पहले दो लोग बोल रहे थे अभी कोई नहीं बोल रहा है
Sir, the temperature at which condensation starts.
right the
First
temperature
liquid
at
form.
which first drop of liquid comes from the vapor right it condense vapor condense होके liquid में आता है that is the saturation pressure and that normally happens early in the morning अगर walk पे गए हो तो देखा होगा आपने एग्जाम्पल पहले भी दिया था मैंने ऑन द लीव्स ऑन द ग्रास सवेरे सवेरे आग जाओगे 5 बजे तो वेट रहता है देयर इज ड्यू ड्रॉप्स इट्स कॉल्ड ड्यू ड्रॉप्स बिकॉज एट दैट टेम्परेचर इन द मॉर्निंग the air becomes saturated with water vapor and excess जो रहता है because at higher temperature जो रात का temperature रहता है suppose in the night it is 30 degrees centigrade and early morning it is 20 degrees centigrade तो 30 डिग्री सेंटीग्रेड पे वेपर प्रेशर ज़्यादा रहता है सेचुरेशन प्रेशर ज़्यादा रहता है तो ज़्यादा पानी रहता है हवा में बट एट 20 डिग्री सेंटीग्रेड इट कैनॉट होल्ड दैट मच वाटर तो एक्सेस जो वाटर रहता है बियॉन्ड द सेचुरेशन प्रेशर इट इज कंडेंस्ड or that appears as dew. Similarly, if I take saturated solution of NaCl in water at 40 degrees centigrade and cool it to say 25 degrees centigrade, क्या हो जाएगा? What will happen if I take a saturated solution of NaCl in water at 40 degrees centigrade and cool it to say 25 degrees centigrade? What will happen?
NaCl के क्रिस्टल्स फॉर्म होने लगेंगे
NaCl crystals form होंगे ये आपको वीडियो बताया था last year, right? That's what we did when we did calculation in PC for crystallization. The solubility of NaCl in water at 40 degrees centigrade is more than that at 25 degrees centigrade. Similar to vapor pressure, right? सॉलिबिलिटी कम हुआ तो एक्सेस जो रहेगा जो डिजॉल्व हो गया था 40 डिग्री सेंटीग्रेड पर NaCl इट विल कम आउट ऑफ वाटर एंड इट विल बी क्रिस्टलाइज्ड गेट क्रिस्टल्स ऑफ NaCl समझ में आ रहा है you understand crystallization now
Yes, sir.
okay so let us start now let us look at thermo point of view it was conceptual so criteria of equilibrium we have seen well any equilibrium we have derived fugacity component in both the phases should be equal right this is what we derived and we said that this is for all equilibria it's not just PLE it's for all equilibria so fugacity in the liquid phase is equal to fugacity in the solid phase right जो crystals बनेगा और जो solution रहेगा and besides temperature and pressure also will be equal right so we can write with activity coefficients equation 1 which we have derived before xi gamma l FIL is equal to Zi is actually mole fraction in solid phase xi is in the liquid phase and gamma I solid phase FIS for solid phase ठीक है equation 1 is okay it's nothing but applying all the equations which we have derived so far so we can write equation 1 in the equation 2 by taking FIL on the right hand side and define a term called psi I which is nothing but ratio of capacity of component I in solid phase to that in the liquid phase. Right? So you know that if you look at crystallization, Xi it will dissolve NaCl water में, right? Xi. You can find gamma I. We have seen equations available. Let's not worry about that. कहाँ से आएगा क्या आएगा? We can find the activity coefficient in the solid phase. What we need to find is psi. Right? If you know psi, then we can find out कि कितना composition रहेगा in the solid phase. That's what we want to find out कि कितना crystallize होगा. Right? So our objective is to find the value of psi I for any particular situation. Okay. So now let us see how to find out value of psi I. So you can write Fi for a solid phase at any temperature and pressure divided by Fi for the liquid phase at any that same temperature and pressure. And we are introducing some term TMI, melting point. Yeah. So we're talking about solid liquid. So we introduce some term called TMI, melting point, and we're talking about fugacity at melting point. So यहाँ पर just numerator denominator same term डाला है, that's why I have shown this arrow. Arrow दिखा है, same term ऊपर नीचे है, cancel हो जाएगा. Ultimately what we get is FIS at temperature and pressure divided by FIS at TMI into and pressure. And then इसमें second term is FIS at TMI and P divided by FIL at TMI and P. Third term is FIL at TMI and P by FIL at TMP. Right? So 3 and 4 are same actually. We just introduce these two terms because we want to get ratios for these. So at melting point, where we get pure component, SLE. If you take a melting point of NaCl and see that there's a solid phase and there's a liquid phase, which is liquid NaCl. Right? At that point, if you apply Vigel criteria, we'll get FIL equal to FIS. So fugacity in the liquid phase is equal to fugacity in the solid phase. So we can say that Fi is solid phase at melting point. Nothing but Fi in liquid phase at melting point 6. Is it okay? So now we substitute equation 6 in 4 and we'll get phi equal to, second term will cancel out. We'll get FIS at temperature and pressure, at required temperature and pressure, divided by FIS at melting point into FIL at melting point divided by FIL at required temperature. Equation 7. Okay. Essentially what is happening is we are saying that this term will okay. Any doubts on equation 7? Now you need to evaluate equation 7. So we need equations for effect of temperature and fugacity, right? Because we're talking about temperature, fugacity at required temperature and fugacity at melting point. And we have defined fugacity coefficient phi I is equal to Fi by Pi. And we also defined residual property of pure component as ln phi I is equal to Gi residual by RT. पहले डिफाइन किया हमने residual property जब डिफाइन किया था. So we can write this as ln phi I is equal to Gi residual by RT plus ln P. Right hand side में लाया तो plus ln P. ln ओपन किया था. So if we take derivative of ln phi by respect to temperature at constant pressure, get question 8 derivative of Gi residual by RT at constant pressure with respect to T. And we have derived this before that HR by RT is equal to minus T divided by D GR by RT by T at pressure and constant pressure and temperature composition. पहले define किया था हमने. What is the effect of temperature on residual crystal energy? So then we integrate equation 8 from TMI to T melting point to the required temperature, and we get this equation integral ln Fi from where lower limit is fugacity at melting point and upper limit is fugacity at the required temperature, to minus HI residual by RT square into dt integral from TMI to T. So if you integrate this, you get ln of Fi at temperature and pressure divided by Fi TMI and T to the minus of TMI to T HI residual by RT square into dt. Or we can write in terms of exponential by taking the exponential Fi at temperature and pressure by Fi at TMI and P is equal to exponential of this integral. That is given by equation 9. Any questions on equation 9? Okay. Then we apply equation 9 to solid liquid phases and substitute in equation 7, which is want actually. इसमें substitute करेंगे because we want value of psi I. So equation 9 for liquid phase is given by equation 10. FRL at temperature and pressure divided by FRL at melting point equal to exponential. Here what we'll do is we'll write residual enthalpy for the liquid phase. Similarly for the solid phase, if we write residual enthalpy for the solid phase. So then we substitute equation 10, 11, equation 7. 11 is this one. Substitute what you get is psi equal to exponential this term, exponential this term, equation 10, 11 exponential terms. And then combine these two terms and we get equation 12, the exponential TMI to T. और ये TMI तो उल्टा है तो पॉजिटिव हो जाएगा. Changing the limits, upper limit and lower limit. What is that? Is minus HIRS for the solid phase minus HIRL to RT square into dt. Questions on equation 12. And there are no questions. Let us proceed. So let us see what is this term minus HIRS minus HIRL. By definition, residual property is nothing but enthalpy, or in this case is enthalpy. Residual enthalpy is nothing but enthalpy of the solution or solid minus enthalpy in the ideal gas. So it is minus HIS minus of bracket HIS minus HIG, and again for HIRL is equal to HIL minus HIG. That is ideal gas. This ideal gas term will cancel out. What is that is HIL minus HIS. Substitute in this equation 12, we'll get psi is equal to exponential TMI to T minus HI is the RT square into dt. So if you know the enthalpy in the liquid phase, enthalpy in the solid phase, integrate from TMI to T and calculate the value of psi, which can be used in the question above. Find out what is Zi. Any questions on this derivation? Can you hear me? Hello.
Yes.
Yeah.
So now we know what is how to calculate psi, and if you know xi, gamma L, gamma s, you can find out what is Zi. That is the purpose of crystallization. What is crystallization giving us? What product is giving us? Any questions?
सर सॉलिड में मतलब मोल फ्रैक्शन कैसे निकलेगा? वहां पे तो वन ही होगा ना, प्योर ही होगा ना सॉलिड।
प्योर नहीं रहता है बिकॉज इट्स ऑलवेज वेट सॉलिड। उसमें वाटर रहता है, उसको बाद में ट्रैक करना पड़ता है। एंड इट कुड बी more than one component. Crystallization में क्या होगा? Suppose I have NaCl and some other compound, right? And here we are talking about Xi. We are not talking about only one component here, right? So it could be that okay, that I have two solids dissolved in, and then both will come out. तो भी हो सकता है ना?
हाँ सर।
It's not just one component. It could be more than one component. Any other question? ठीक है। So this इसमें भी generally क्या होता है? Just normally a short note on SLE. Or they say derive this equation for psi. Sometimes they say derive this equation for psi. So let's move to the next topic, which is solid vapor equilibrium. Solid vapor equilibrium कहाँ आता है? Any example, do you know? Any idea? कुछ तो करते हैं हम। सब्लिमेशन याद है किसी को? कोई पढ़ा था? I want to remember sublimation. What is sublimation?
Solids are converted into vapor.
Okay. Any example देखा है?
Sir, camphor.
Camphor. Okay, और?
Naphthalene balls.
Naphthalene balls. So there are many examples which go directly from solid phase to the vapor phase without going through the liquid phase. Okay. So there are triple points. Solid can go directly from the and directly vaporize, and that is what we are going to look at, sublimation. Heat pressure temperature diagram says CET1 में पढ़ा होगा आप लोगों ने, right? पढ़ा कि नहीं CET1 में? PK diagram.
हाँ
नहीं पढ़ा गया,
पढ़ा है सर।
right? So this is a solid region, this is a liquid region, right? The triple point where all these three meet together, the vapor phase. This is sublimation part. So that means it's going directly from the solid phase to the vapor phase. Normally क्या होता है? Solid to liquid जाता है, then liquid to vapor जाता है. The normal route, right? When you take water, ice लिया, melt होके liquid बनेगा water, बाद में evaporate होके vapor region में जाएगा. But what happens in the sublimation, that directly from the solid phase goes to the vapor phase. ठीक है? समझ में आया? Okay. So equilibrium pressure, in this case it's solid vapor saturation pressure. जैसे हमने देखा vapor pressure के लिए VLE के लिए E sat रहता है vapor pressure. In this case, the equilibrium pressure similar to that VLE का P sat. P sat is also called P sat here. So consider pure solid component 1 in equilibrium with binary mixture of component 1 and component 2. जैसे naphthalene लिया हमने, right? Solid रखा हमने कहीं पर. So vaporize, okay, it will go into air, right? So solid is pure naphthalene, like camphor, villia. Solid is pure, but vapor phase, which is in equilibrium with the solid, is not pure. It is a mixture of air and that component. So component 2 is insoluble solid. That means air does not dissolve in naphthalene or camphor, right? Whereas camphor or naphthalene dissolves in air. You can say in terms of NaCl in water, this is a solution. Right? So component 2 is insoluble in solid phase because solid phase is pure solid, right? And कंपोनेंट 2 जैसे एयर लिया, राइट? नैफ्थलीन बॉल्स का कॉन्सेंट्रेशन जो रहेगा, नैफ्थलीन का एयर में जो कॉन्सेंट्रेशन रहता है काफ़ी लो रहता है, राइट? बट एयर में मैक्सिमम रहता है, सो मे बी 99.9% इज एयर, 0.1% is naphthalene there. The major component is air in this case, and hence we call it as solvent, similar to crystallization. And component 1 or naphthalene is called solute. जैसे हम बोल रहे थे NaCl डिजॉल्व कर रहे हैं वाटर में, NaCl is solute and water is solvent. Similarly, here we are considering solid vapor equilibrium. We consider naphthalene or camphor as solute and air as solvent. Okay. So we take Y1 as mole fraction of component 1 in vapor, right? Or in other terms, we can say this is the solubility of naphthalene in air. Maximum water you can take, we said talked about that will be PSAT. So what is the objective of doing SV, solid vapor equilibrium? To compute what is the mole fraction of naphthalene or camphor in air as a function of temperature and pressure. Right? Yes, it considered already this naphthalene as solute and air as solvent. And if you look at equilibrium, you know that for component 1, viscosity in the solid phase is equal to viscosity in the vapor phase. Solid phase में प्योर है तो प्योर कंपोनेंट viscosity रहेगा, एंड वेपर फेज में दो है, एयर है और naphthalene है, तो इट इज viscosity of component I in the solution, F1 bar V. Okay, and only one phase equilibrium equation, right? You cannot write for the liquid solid for the other component, component 2, because component 2 is not there in solid phase. Air is not there in the naphthalene or camphor, so you cannot write for component 2, right? You can write only for component 1. Okay, any questions on question 1? So now we use a pointing equation. Pointing equation was essentially calculating what is the effect of pressure on viscosity coefficient or viscosity, right? So we had Fi is equal to Phi sat Pi sat into exponential VIL P minus Pi sat upon RT. Again, we talked about equilibrium. We didn't say it is only VLE, right? It can be any equilibrium. So for solid vapor equilibrium, you can write this same equation, pointing equation, as Fi for the solid phase is equal to Phi sat into Pi, F1 for the solid phase component 1 के लिए equal to Phi1 saturation, P1 saturation into exponential P1s P minus P1 sat upon RT. And P1 sat is nothing but solid vapor saturation pressure at that particular temperature. And V1s is the molar volume of the solid. For liquid tha, like VLE, it will be liquid. For solid phase, we will take V1s. And we know that for vapor phase, F1 bar V, or viscosity of component 1 in the vapor phase, is equal to Phi1 into Phi1 bar into P. We've done this before, right? If we combine 1, 2, and 3, equation 1, but viscosity equality, equation 2 is the pointing equation, and equation 3 for the vapor phase viscosity. What you get is F1 bar V is equal to FIS, as equation 1, equal to Phi1 bar P then equal to equation 2, which is pointing equation. So 5 1 set P1 set exponential P minus P1 set upon RT. So we can write now y1 is equal to, from here, P1 set upon P into phi 1 set upon phi 1 bar exponential V1 is P minus P1 set upon RT. Any questions on equation 4? We just combine those three equations and written in this form. Or we can write this as phi1 is equal to P1 set upon P into F1, where F1 is nothing but this term. Phi1 set upon phi1 bar exponential V1 is P minus P1 set upon RT. Do you recall this equation, this type of equation? क्या था ये? We've seen this type of equation before, right? देखा है PLE में y1 equal to P1 set upon P into something. नहीं आ रहा किसी को? What is Raoult's law? Raoult's law भी याद नहीं है क्या रे? What is Raoult's law?
P1 bar equal to y1 into P.
ये Raoult's law कब से हो गया रे? What is Raoult's law, Devendra?
P is equal to x1 into P1 set plus x2 into P2 set. डेल्टन्स लॉ में हमने पुट करके वैसा नहीं.
इसको याद नहीं है. दीक्षिता?
P1 bar equal to x1 into P set.
यही है ना वही तो, right? P1 bar is y1 into P and x1 into P set is this, right? So this is essentially your x1. है कि नहीं? ठीक है, तो याद रखो, थोड़ा बहुत याद रखना ज़रूरी है. Okay. So now F1 is nothing but representing vapor phase non-linearities through phi 1 set and phi 1 bar, right? And for low pressure, both the effects are negligible. We have already said with low pressure it becomes like ideal solution or ideal gas. So for low pressure, F1 is equal to 1 हो जाता है. So just said pointing correction factor is 1 at low pressure, and at low pressure phi 1 bar is equal to phi set. So what you get is y1 equal to P1 set upon P. और ये इक्वेशन कहाँ देखा था हमने? कहीं देखा है? ये देखा ये इक्वेशन का, इस टाइप का इक्वेशन P1 सेट अपॉन P क्या होता है रियली में?
Gamma.
Gamma, right? So there is similarity. You'll always see some similarity somewhere. VLE, SSE, SV वगैरह कहीं ना कहीं कोई कुछ सिमिलर मिलेगा आपको. ठीक है. If I know the vapor pressure of or saturation pressure of naphthalene and I know total pressure, I can find out what is the mole fraction of naphthalene in the air. At low pressures. हाई प्रेशर के लिए हमारे को करेक्शन फैक्टर लगाना पड़ेगा, पॉइंटिंग करेक्शन वगैरह वगैरह करना पड़ेगा इक्वेशन 6। ठीक है, एनी क्वेश्चंस डाउट्स ऑन एसवी? इसमें भी जनरली कुछ शॉर्ट नोट ही आता है, ज़्यादा कुछ नहीं आता है। They'll ask you to derive equation for f1 or y1, something like that. Okay, so if there are no questions, let's move to the next topic, which is osmotic pressure. What is osmotic pressure? पता है किसी को? ऑस्मोसिस कभी पढ़ा है आप लोगों ने? ऑस्मोसिस नहीं पढ़ा है कभी?
सर वो शायद फ्लो ऑफ सॉल्वेंट फ्रॉम लोअर कंसंट्रेशन टू हायर कंसंट्रेशन।
ओके, आप लोगों के घर में वाटर प्यूरिफायर है किसी घर में?
यस सर।
किस टाइप का वाटर प्यूरिफायर है?
आरओ सर।
आरओ। आरओ क्या होता है?
रिवर्स ऑस्मोसिस।
हाउ डज इट वर्क? हाउ डज इट वर्क? आपको गंदा पानी डाला तो प्योर वाटर कैसे मिलता है? कभी सोचा है इसके बारे में?
सर उसमें मेम्ब्रेन होते हैं ना, तो फिल्टर कर जाता।
मेम्ब्रेन होता है, फिल्टर कर देता है क्या? ठीक है, कितने लोग के घर में आरओ है? हाउ मेनी पीपल हैव आरओ एट होम? रेज देयर हैंड्स। ओके, सो जिनके घर में आरओ है, go home and find out how does it work. Okay, and come and tell me tomorrow. ठीक है? So let us understand what is osmosis. Okay, so if I take a container with a membrane, this is a membrane, right? Let's say, and if I put water, pure water on one side, and a solution, any solution in water, it could be NaCl, it could be anything, doesn't matter, matti, kachra, kuch bhi डालो, impurities, right? So what will happen is, naturally, if I just keep like this, what will happen is water will go from pure water to solution, और pure water नहीं मिलेगा. If I keep like this, membrane डाल के एक साइड में pure water डाला मैंने, tap water या pure water, और दूसरी साइड में मैंने solution of NaCl in water डाला, suppose थोड़ा mix करके impurities डालने के लिए. What will happen is, after some time, naturally, what will happen is water will go towards solution. इधर से नहीं आएगा, water will not go from here to here. This will not happen. Naturally, water will go from pure water to solution. Why is that? Why is that? Any idea?
कंसंट्रेशन बैलेंस करने के लिए दोनों साइड।
या मास ट्रांसफर में क्या पढ़ रहे हो आपने? क्या पढ़ा मास ट्रांसफर अभी तक आपने? कौन से टॉपिक्स पढ़े अभी तक आपने?
The diffusion.
डिफ्यूजन कैसे होता है डिफ्यूजन?
From higher concentration to lower concentration.
सो हायर कॉन्सेंट्रेशन लो, इसमें हायर कॉन्सेंट्रेशन कहाँ पर है?
The solution side.
सॉल्यूशन साइड में हायर कॉन्सेंट्रेशन है, तो फिर उल्टा क्यों जा रहा है पानी?
तो शायद मेम्ब्रेन की वजह
शायद मेम्ब्रेन की वजह से मास ट्रांसफर चेंज हो जाएगा क्या?
से।
एनी गैसेस शरायु बड़े आपके घर में भी है ना आर ओ? We say if I take this is pure water, right? What you are saying is this is pure water, right? Pure water यानी concentration कितना होगा वाटर का? X कितना होगा वाटर का?
1.
1.
इधर क्या है? Suppose I say it is NaCl solution, NaCl in water, तो यहाँ पर X कितना होगा वाटर का?
तो डिपेंड करेगा.
हाँ डिपेंड करेगा कितना होगा. इट विल बी 1 और मोर देन
Less than
और
1.
लेस देन.
Less than 1.
तो किधर कॉन्सेंट्रेशन ज़्यादा हो गया?
सर प्योर में.
Right, and that is why water will go naturally in this direction, because concentration here is more, concentration here is less by or what you have said in mass transfer, right? But what we want is we want other direction, right? और ये नहीं चाहिए हमारे को, उल्टा चाहिए हमारे को. एक्चुअली प्यूरिफाई करना है सॉल्यूशन, NaCl रिमूव करने का और वाटर प्योर चाहिए. तो व्हाट यू डू इज यू अप्लाई प्रेशर हियर. You apply pressure here so that the direction of mass transfer changes, right? So in situation A, chemical potential of pure solvent is more than that of chemical potential of solvent in solution. That is why mass transfer takes place. Ultimately, chemical potential is a driving force. हमने देखा था, right? सर में हमने पढ़ा है, right? Chemical potential is a driving force, not concentration. Concentration can be correlated with chemical potential, but ultimately the root cause is chemical potential. So in this case, mu I of pure water is more than that of solution. That is why mass transfer will take place from pure water to solution side. Now what will happen is when I apply pressure here, chemical potential of solvent in solution increases. हमने देखा था, right? We have seen effect of pressure on chemical potential. T mu I, double mu I by double T at constant temperature and composition is V1 Vi bar, which is partial molar volume. Right? So at some pressure P point, P prime, some value which is higher than atmospheric pressure, the chemical potential of solvent in solution, that means in this side, will be equal to chemical potential of pure solvent at pressure P. Right? जितना भी यहाँ पर है, suppose let's say यहाँ पर जो है, suppose I say it is mu I P and it is mu I in the solution, right? At some point, this will be equal to this. I keep increasing the pressure बढ़ाते जाऊंगा till this is equal to this. Right? यहाँ पर पहले था mu I is greater than mu I P pure. Let's say pure is greater than mu I in the solution. So So I want to increase the pressure here so that I equalize the chemical potential on this side and this side. So what will happen in that case when the chemical potential is equal? What will happen when the chemical potential on both the sides is same or equal?
Equilibrium.
हाँ?
Equilibrium.
Equilibrium हो जाएगा, right? That's the condition of equilibrium, right? At equilibrium, your chemical potential has to be same. So that means there is no mass transfer happening. पहले यहाँ से इधर से pure solution में जा रहा था, that will stop, right? There will be no mass transfer from water to solution. And if I increase it further, more than this one, greater than this one, then what will happen? This will be this will be greater than chemical potential of pure solvent. And then what will happen? The mass transfer will take place from this side to this side. And water will go from the solution to the pure solution, pure water. समझ में आया? Okay. So when it is equal, there is no diffusion taking place, and at pressure P prime, which is greater than the direct at pressure P, which is greater than P prime, the direction of diffusion is reversed when solvent diffuses from solution to solvent. Right. So first one, which is when water is diffusing from pure solvent to solution, is called osmosis. Naturally occur होता है ये first one, और ये is called reverse osmosis. Right. When solvent diffuses from solution to solvent, it's called reverse osmosis. That's why we call it reverse osmosis. उल्टा कर रहे हैं डायरेक्शन हम मास ट्रांसफर का. And excess pressure, which is P prime minus P, to be applied over the solution at constant temperature to arrest the process of osmosis called osmotic pressure. इतना minimum pressure चाहिए to stop the mass transfer from pure water to solution. और उससे ज़्यादा चाहिए to get pure water from solution. ठीक है? Any questions on this?